Good morning and welcome. Thank you for joining me. Just wondering, anyone from my last year's talk here? Probably a couple of people. Thank you. So, this talk is about deep learning. There are some related topics. There is going to be another talk on machine learning in testing and another one on TensorFlow. So please check them out. My name is Kheyrollahi. I'm a solution architect for a company called ASOS. We are about to become UK's largest fashion retailer, overtaking Marks & Spencer after so many years. What I do is I look after the recommendations platform. I work on data science with data scientists. And what we do is we turn user interactions into personalized experience using machine learning. Now, I've always been interested in the field of machine learning, but I formally got to work on the problem of detecting road marking and text recognition. And here is a sample of the code. As you can see, the application back in, back in 2008, basically recognizing the text and marking on the road, as you can see at the top. And on the left, basically what it does, it calibrates the camera by finding the vanishing point. The detection happens in real time. The project was pretty successful. It resulted in publishing 2 papers, one of which has got more than 50 citations, which is not bad. I use 3-layer neural networks for this project, and this project, basically, some of the techniques I use are completely obsolete by deep learning, which I'm going to explain. The code for it is very much on GitHub, so don't worry about the code of the projects I'm going to show. They are all there. Since then, I've been focusing mainly on machine learning, on text, and natural language. So without trying to sound dramatic or revolutionary, there is no such thing as deep learning. Basically, yes, it's as simple. Deep learning is a culmination of various technical and non-technical events which made techniques that we've known for so many years, and some of them for decades, become successful. So deep learning is essentially a rebranding of multi-layer neural networks. Now you might ask, why such a powerful thing needs rebranding? Well, we'll get to that. So, this talk, I'm going to explain the building blocks of deep learning when they happen through the history. The focus here, bear in mind, is not the history itself, but why it took so many years for us to get where we are. And after that, I'm going to talk about where we are, the state of the art, and where we are going with deep learning. And next one is basically, I'm going to break down a realistic example, something that probably you've seen on GitHub happening, that they recognize, the format, the language of the project. We're going to look at that realistic example. You might have some expectations in terms of things that you might see here. I'm just leaving the pointer. Unfortunately, you won't be able to cover them. One of them is Deep Dream. You probably have noticed these pictures with faces of cats and dogs embedded in them. That's Deep Dream, taking a neural network and just providing the input, the out, reversing the input basically to get the other image. The other one was the AlphaGo, beat the world champion. That was Monte Carlo tree search, if you want to have a look. And most interesting one is GAN, or General Adversarial Network, which is a very, very hot topic currently. You probably might have seen, they take a picture, turn it into a painting by Van Gogh or Monet or someone else. And this is This is quite cool. Now, the history. The history of deep learning is utterly interesting. And as we navigate through history, you will find out that it is as much about the people themselves than the technology. It's about, you know, their unusual talents, about the challenges they faced, you know, being rejected by the academic community. You know, sometimes the demons they were facing inside. But it's going to be interesting. Are you ready? Thank you. It's a cold winter. Two people are warming themselves by the fire. One of them is drinking whiskey and eating ice cream. This is what he really enjoyed. He is quite a bit older, and at this time probably looked something like this. He comes from a wealthy background. He is a neurophysiologist, physician, philosopher, and a poet. It is his home, and he later became one of the founding fathers of cybernetics. The other man is much younger. He's barely 18. And, well, we said it's not his home. In fact, he doesn't have a home. He's homeless. Doesn't mean that he's a hobo. He actually got a PhD position from the University of Cambridge from none other than Bertrand Russell when he was, guess what, 12. Well, he had to reject that. And the story goes as that he was being bullied at school all the time, and one day he actually had to flee from the guys and hid in the library. And at that time, managed somehow to stay in the library and went through one volume of a book called Principia by Bertrand Russell. He found it so interesting that he finished the 3 volumes over the next 3 nights. And he found some errors in the text, as you would do as a 12-year-old. And he decided to write a letter to Bertrand Russell. He didn't expect much to come out, but in fact, Russell replied back and asked him to join immediately in Cambridge to start his PhD, which obviously he could not oblige. But 3 years later, when Russell went to the University of Chicago, basically he left home, and at the age of 15, never to come back. In the University of Chicago, he met a young medical student, and this guy basically was much more interested in going to Russell's lectures than studying his own stuff. And he introduced Seymour McCulloch to Pitts. And at this time, McCulloch was a seasoned, established scientist, and Pitts was a runaway 18-year-old. But the trio clicked, and this was the start of collaboration and friendship which would shape the discoveries leading to deep learning. And these guys were friends, discussing philosophy, poetry, and Pitts and McCulloch living together, and in fact died the same year. So McCulloch was really interested in finding, in looking at the neuron and seeing how it basically needs a threshold in order to fire. And he was so fascinated by how he can use that as a unit of logical circuit. But his grasp of maths wasn't great. And this is where Pitts would come in. And basically, they set out to devise a neuron, an artificial neuron, as a unit of logical circuit. And they published this paper, without which we wouldn't be here talking about deep learning. This paper was published in 1943, and after which Pitts went to work in MIT working for Norbert Wiener. And 1951, the rest of the gang joined him. and they started working on some very exciting things, and basically Pitts started working on 3D neural network. We don't know what it would be, because I will mention later he burnt all of that, but could have been describing what our current deep learning would look like. And Letvin has this to say about him. In no uncertain sense, he was the genius of the group. Sadly, in 1952, Wiener clashed with McCulloch and broke all ties with McCulloch and anyone who had anything to do with him, including Pitts. On one hand, Wiener was at heart an engineer, really, really interested in building stuff. And he actually went to become one of the fathers of robotics. Also, it was mentioned that his wife hated McCulloch. All around, this had a terrible impact on Pitts and made him basically socially isolated. Doesn't mean that he didn't do anything. The trio did this seminal paper describing how analog signals from the eye actually does part of the vision. So it's not just the brain. And this is an idea that we see in deep learning getting confirmed. But anyway, after this, basically he burnt decades of his unpublished work, including his 3D neural network. So all this theory was good, but some people started building neural networks and training them. One of these people was Frank Rosenblatt. He started in 1957 and kind of took Pitts' model and started little changing that and called it Perceptron. And Perceptron, in 1958, he published a book, and 62 basically, 58 a paper, and 62 a book. And we can see what he does here.
He's using it to explore the mysterious problem of how the brain learns.
This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
Right. So this is what they were doing back then. Now, just to recap, you guys, what you saw was basically providing examples. That is called supervised learning. And supervised learning essentially is providing labeled data to a model and let it train. Unsupervised learning, on the other hand, is that you let the network basically learn the patterns of the data. And in the middle, there is reinforcement learning, which you don't give it basically the labels, but every time, every iteration you train, then you tell the network how good or bad it's done. For example, you've seen these agents playing Mario. So this is essentially reinforcement learning. So what is a perceptron? Perceptron, we talked about it, is basically inputs, weights. You generate the weighted sum of the inputs, you pass it to an activation function, you get the output. All of this, with this training, you can do in less than 20 lines of Python. Now, I'm not going to go through the code here, but just want to bring an example just to make sure that we're all happy with it. So I've got this input vector. I need to create a sum. What is the weighted sum? 6 multiplied by 2, 3 minus 1, so on and so forth. And provide it, because minus 1 is less than 5, is not more than 5. So basically, I will return 1. Now this one, you decide. So weighted sum becomes 24. You turn 0. It's as simple as that. And this is essentially the building block of the deep learning that we're going to look at. So what would you use for activation function? well, pretty much anything you want. But these are some of the common activation functions. The sigmoid, tanh, the ReLU, this one, is currently the hottest activation function. This is so simple, but this is essentially was revolutionary. So, when teenage Rosenblatt was studying in Bronx High School, he met a boy called Marvin. And this particular Marvin and Frank Rosenblatt, they grew to become rivals. And Marvin Minsky, in fact, apart from having arguments in conferences with Frank, like very loud, although he has been working on neural networks since 1951, he published this book in 1969. And that year couldn't have been more symbolic, because also Pitts and McCulloch died same year. But they arguably, they believe this book, Perceptrons, basically killed the AI research for the next 2 decades. So it's called the first winter. So this book wasn't groundbreaking or anything. It wasn't even accurate. But what it did say is that you can't model a neuron to do an XOR problem. And even McCulloch and Pitts knew that you could solve this problem actually using more layers, but somehow, freaked the community and they stopped working on it. And that continued until 1986. A British scientist called Geoff Hinton, with a couple of colleagues, they found a way to train multi-layer neural networks. That's called backpropagation. And this young scientist started from physiology and physics, studied philosophy and then psychiatry, and then became a carpenter, and so all it goes. But basically, he made multi-layer neurons a possibility. And one of the people who actually built something really, really interesting was Lac Kun, a Frenchman, which basically his digit recognition was revolutionary. And he did something else. He found convolutional neural networks, although it's debatable whether he found it. So what is a convolutional neural network compared to Perceptron that we've seen? Although it uses kind of the same concept. So what it does is essentially is a convolution over the inputs. Now, what is a convolution? For those of you who might not know, it's very simple. You got a kernel, and this kernel, for example, is 3 by 3. You can see here. And then what you do is multiply each one with the neighborhood, and you come up and fill this in. And this is basically, ideally, is explained here in this animation. It's not rocket science. It's very easy. Just some multiplication and summing. But the second winter was coming. Yes. So what was the problem? So they said, okay, I've got these, let's say 64 by 64 picture. That's a very, very small picture by our standards. But that is already more than 3,000 dimensions. And what you do is that the data gets diluted across all these dimensions. This is one of the few books I actually own on the subject. And its importance probably very much historic now. But he really describes this problem very well. So it says, if you're forced to work with a limited quantity of data, as in practice, then dimensionality basically says very poor representation because data becomes very sparse. So you end up solving that problem, reducing dimensionality. What do? So they said, I've got this picture that is 64 or 60. If I can extract some features from it, then maybe, that will be much smaller and that problem would go away. So they started doing feature extraction. And this is, sorry, I jumped. So, for example, this tree, I can describe this tree by having 3 loose ends and also a particular aspect ratio, and I can start describing and create a much smaller feature vector. What is the problem with that? First of all, it's very susceptible to noise. What is the other problem? This is admission of self-defeat. On one hand, you say, okay, I've got a neural network. I'm trying to replicate the biological brain by building this neural network. And what I do is that, I provide these kind of arbitrary features. No sane person would ever, start counting the loose ends of the word 3 character. There was another problem, overfitting. So they realized for simple problems, it was working great. For difficult problems, they knew that they had to build multi-layers and build deeper networks. But they found that when you do that, the system does really well on the training data, but it can't generalize. You give it the data that it hasn't seen, it just flops. And that is essentially known as overfitting. What is the problem? The problem is that the network doesn't just learn the data, also learns the noise. And this picture from the same book is quite interesting. So that's why when in 2008 I was doing my research, they said, don't do like many layers. It's never gonna work. Just do it, maybe single layer is gonna work better. So there were some other problems as well. And one of them, so we talked about curse of dimensionality and overfitting. Another problem with trainings would never converge. And you wouldn't know whether it's ever going to converge, or, I need to just leave it for more days, or it's just a problem. And sometimes you would start the training and then all the weights gradually go into 0. Guess what? Multiplying something by 0 results in 0. So basically, the training would stop. And we talked about the feature engineering, and they found some other kernel methods, such as support vector machine. Anyone used support vector machine? Yeah, a few people. So this has been doing very, very well. And people basically said, just forget about neural networks, just use this. But that was not all the story. So during all this time, there were still people believing that neural networks, there isn't a structural problem. The problem is mainly just we need better techniques. These are technical issues we need to get around. And these 3 people are known also as 3 Musketeers or Canadian Mafia. And the reason is that they started working around early 2000 in Canadian Institute for Advanced Research, or CFAR. And basically, they carried on believing. But they couldn't really publish any paper. The papers would be rejected. In fact, you will see 1998 paper from Lac Kun. Basically, he had so much difficulty while it was really revolutionary. So, about Lac Kun, this is what his colleagues would say. We felt we had to invite him. His models he's talking about, he's been working for years. They really never showed anything. And this is what the advice to researchers going to work on Hinton's lab. Smart scientists go there to see their careers end. This is from Yoshio Bengio. Said, I had to twist my students' arm to work on neural net. They would fear that their papers would be rejected. And in fact, quite a bit of them were rejected for all the wrong reasons. But they still believed. But the revolution was about to happen. And first of all, 1998 from paper from Lac Kun and Bengio. Basically, they described the gradient descent algorithm, which is like the most popular currently algorithm for training. And this is not rocket science. This is, they said, you know, when we train the network, instead of giving all the data, just give it batch by batch. And it produced really great result. Another thing that Geoff Hinton did, said, you know, they found that initializing these weights, they would initialize all of them to, you know, some random number or whatever. They found that actually using some unsupervised learning to initialize them, like Boltzmann machine, has a terrible, has a very positive impact and can reduce the time to do the training. There were other things. GPU, everyone probably knows now that GPU is so revolutionary. Hinton's paper, he wasn't the first one that used GPU. There were other people as early as I remember that people were talking about GPUs back in 2006. ReLU, that's simple, you know, f(x) equal to max x or 0. You know, how revolutionary is that? You know, but that's rectified so much of the problems that a neural network had. And they found, yes, it actually works. The only thing is that we needed better techniques, just some modification. So, how did we get around the second winter problems? Remember, the data would dilute. What would you do? Give it more data. And that's where big data, the companies that have lots of data is so important. Overfitting, what they said is that every time I'm going to hide part of the data so that my network never sees and randomly just keep changing it. So the network gets ready to basically not see some parts of the neuron, the input, and still get trained, and that improved the generalization. Trainings never converged. We talked about the weight initialization as well as using GPU. ReLU, again, you know, because of that kind of max effect, helped to kind of make sure decay of the weights don't happen. Stochastic gradient descent, you know, and pooling. So pooling is another technique, and essentially, I've got a slide later, and what it is basically looks at the input in the neighborhood and takes the max of them. You know, that's really all it does. This is as simple, you know, these are the techniques that they use to solve these problems. So, where are we now? In 2012, AlexNet, for the first time, Alex Krzyzewski, Geoffrey Hinton, Ilya, they got error rate of 15.4 of ImageNet, which is detecting various objects. It is a very hard data set, and they got this. And what they did was they used 9 layers, 5 to 6 days on 2 GPUs they trained, and they used ReLU. And we look at what they use. You see pooling, max pooling here. The next year, ZFNet, again they used 9 layers. What they changed from that, because the AlexNet, they used a kernel, remember, for convolutional. Instead of using 11 by 11 kernel, they used 7 by 7. You know, changed some parameters, and they got better results, 11.2. And that's their network. The VGGNet, they got even reduced even further. And that was very interesting because they said, actually, we're going to use 3 by 3 and it's going to work. Just to show you what I mean by the kernels, I just want to make sure that we all clear about this convolutional, because this is what we're going to use. So again, this is what we were talking about, the kernel. So AlexNet used 11 by 11. The next one used 7 by 7. And then they use they saw that 3 by 3 is sufficient. So where were we? Okay. All right. So next one was GoogleNet. They introduced, this is the era, and they had 100 layers, but they introduced something else very, very interesting. They called it Inception Module. Guess why? Because of the Inception film, you know, they had to go, like, we need to go deeper. So they built this Inception Module, which essentially was the convolutional nets, which we described, but in parallel. And they had different, for example, kernels, and they would, at the end, concatenate all of that. And that was, and you can see these modules here. And this is the whole 100 networks, and you can see these modules. And you can see concatenation, pooling. They use average pooling as well. And this is what essentially they use. Next one is the ResNet from Microsoft Research Asia. They had 153 layers, so everyone just would go deep. What they did said, you know, in addition to these convolutional intermediate layers, I will keep the original input in the input to the next layers. That's what I do. And this is basically, they came up, and the error rate went to 3.6. So where are we going? Geoff Hinton basically says, start from the beginning. One of the biggest contributions he's made is backpropagation algorithm. He says, just get rid of that, build something else. We need to start from the beginning. And as I explained, unsupervised learning is very hard. They try to work on ways of progress that. GAN has been very promising, as well as the autoencoders. So this is all well and good. What we need to do is basically discuss the programming language detection. So this is what I did. I chose 16 programming languages. I collected 2K per language from GitHub. That 2K is not really enough, you know. It's enough to make a point and show you a working example, but really, essentially, I need to, you know, like go maybe 10 times at least of this number. I'm using Keras on top of TensorFlow. So Ashik is going to be talking about TensorFlow this afternoon at 2:20. So if you are more interested, have a look at his talk. I trained it on a GPU machine. And it took around 8 hours to finish. So you always have a training data and testing data. I had the 1K testing data, and I use Python. All the code is basically here. I will publish the slides right after the talk, so don't worry about it. You'll have access to it. So in order to make it a bit, I mean, detecting language is not really that hard a problem. But I just wanted to make it a little bit more interesting as well. So I use Jan Laocoon's 2016 paper. So anyone has done text processing, text machine learning? Yeah, a couple of people. So in text, usually what you do is that you break the document into words. I use completely different approach, and this is the approach from this paper, which basically what it says, forget about words, and you just look at the characters. And this, you could see why it could be beneficial in my case as well, because a lot of syntactical rules basically apply to brackets or special characters that basically are completely taken away if you are doing you know, just by words. So so what I did, basically I just used, these are the 70 characters I kept, you know, I turn everything and use only these characters, and then I turned every character into a one hot vector. And this is something that you're gonna hear a lot. If you do machine learning, you're gonna hear a lot. So what it is essentially is that length of 70, an array of 70, and you keep one of them 1, the others 0. And this is how you do the categorical data. It's very, very simple, right? And for example, this is how it's going to come out. If I have import numpy as np, this is the import word. You know, I'm not sure if this is the exact right place, but just to show that, you know, the I, which is 9th character, is going to be 1, and like that, you know, RT and all of that. This is, and you just concatenate these. And I took 2K of the data and just concatenated these 70 characters. So this is the architecture I've used, and I'm going to explain. So we have dropout initially, so that we get rid of overfitting to a large extent. I have convolutional 3, 5, 9, and 19. These are basically the kernel size. And after that, we have pooling. At the end, we concatenate. This is the Inception module. And then I have dense. What is a dense? Basically has connections from every input to every output, right? And then I put another dropout. So the dense are very good in generalizing, while the convolutional is very good at finding the local input data, because it's actually built on top of the way that neurons basically work. And that's why it's important. At the end, you use softmax. Softmax essentially turns numerical numbers into likelihood. So at the end, I will have 16 outputs, and each one gonna say what is the likelihood, and I'm using softmax. That's as simple as is. My input number of characters, I said, you know, up to 2K, and character dimension is 70. And output number of classes, which I have 16 class or 16 languages. So this is max pooling. It's not rocket science, but essentially a 2x2 max pooling will result in just getting the max of the neighborhood. So we talked about convolutional dropout. You know, it's basically randomly, semi-randomly, it masks the input. Convolutional, we talked about it. Pooling, we said it's just usually max pooling. Dense, generalize the features. Softmax turns scalar to probability. Right? Probably you want to see, look at some of the demo, and I'm going to right. So this is basically essentially running in my machine. So give me a GitHub library that you want to go to. I mean, I can show you something now. For from my own, but these are not, I mean, I randomly got the data. You can see how I got the data, but this is essentially, if I go to raw, get this, right, should be able to give me what it is. Right, this is C#. So someone shouts out a GitHub project. Spark, okay. Spark GitHub. Right, GitHub Spark. Right. Core. No, that's POM. I mean, I can go to, sorry, I don't want to blame anyone for this. Just raw. I mean, this is, let's go to, this is the XML. And I can provide actually the, oh, that's the, I can provide the URL. Right, that's XML. Now I could go to source and get test main. Yeah, Spark. That's Java. That's a small file, but anyway, I'm gonna risk it. That's a very small file. I mean, I think it won't be able to find it. Scala, yeah. Sorry? I'm missing, sorry? The last, oh, the last. Yeah, I don't think it makes much difference. Let me go Spark. I mean, on smaller ones is doesn't do as well. Sure, it's definitely like PHP. When I removed the first few lines, so it actually, one of the things that I haven't trained it on the snippet, so it doesn't generalize. You've only seen files. That's why it can do only files. But if I give it, for example, a PHP file, it's not going to be able to do. R, obviously, this is, okay, let's look at this. That was a shell. Yeah, that's a bash. It does pretty well. I mean, the point was to illustrate. I think what I need to do is to introduce another layer in between. After the first convolutional, have to have another convolutional. So I appreciate that it's very hot in here, and I'm baking. But just to leave you with this, as we said, that's what Hinton says. Start from the beginning. Do you have enthusiasm? This course from Geoffrey Hinton is free on Coursera. And everything you need is there. You just need the machine.